Hello, welcome back. This is lesson 4.3, multiply polynomials. So guess what we're going to do? We're going to multiply polynomials. So last time we talked about adding and subtracting polynomials. This time we're talking about multiplying it. So our real world kind of idea. Every day, all over the state of Texas, oil wells are producing crude oil. And they give us an equation right here. Okay, so then, of course, what kind of mathematical question? We can talk about things like this equation, by the way, is how many oil wells are in Texas. So we can also talk about how much oil does each oil well produce. We can even start talking about cost, things like that. But we need a bit more information, right? So here we go. So here's our original equation. This is the number of active oil wells in Texas, and each oil well produces about this many barrels of oil each day. And so from there, we can figure out how much oil is being produced on a daily basis. So, if we had let's say two refineries that are working, and each one of them produced 60 gallons, how many total in one day, how many total gallons of oil would we have? We just multiply them together, right? So now that we just have complicated expressions, what are we going to do? You guessed it. We can multiply them together. And that would essentially give us total number of barrels being produced on a daily basis in the great state of Texas. So let's figure out how to do that. So before we get too far in the weeds, one of the main things that we use, the idea of a product of two binomials, is in the idea of area or even volume. And so it's actually a really good way to visualize it. So first of all, we got another vocabulary word. So a binomial is a polynomial with two terms, and you can represent it as two binomials. I'm sorry. You can represent it as the product. The polynomial you can represent as a product of two binomials. So that's going to make more sense in a little bit. So if we look at our rectangle, so I'm sure all of you remember the area of a rectangle is length times width. So you'll see that right here. And you can also express this, the area of a rectangle, as a polynomial. So like x squared plus, whatever, x plus whatever. And so you'll see that written right here. So a visual proof behind that is you can break up this rectangle into different sections, and then the area of this whole rectangle here is just the area of this little rectangle, this one, and this one, all added together. And so if you do all of that, you'll get this, and then you'll eventually end up with our polynomial. So this part is the binomial, this part is the polynomial. So that's just one of our vocabulary words that we kind of should keep track of. So you can do the same with volume as well. Just volume adds another dimension, length times width times height. So we can do that with this guy, length times width times height. So we're going to get our binomial, because it's a product. And then we can also figure that out by finding the volume of each individual piece within this rectangle. And so when we work out all that math, we will come up with a similar situation with right here. It's the volume of the first rectangle, the second rectangle, third rectangle, and fourth rectangle all added together. So you can do that. You can find the volume of all of those things. We're going to skip right over into multiplying binomials and polynomials together, because I think once you know how to do that, this will be a piece of cake. So let's do it. All right, let's get into the nitty-gritty. So when you multiply polynomials, this chart is how you do it. So you've got two monomials. Remember, a monomial is, something like this, where you only have the product of a bunch of stuff, no additions or subtractions or anything like that. When you're multiplying these together, now if you've taken chemistry or a science class, you probably have seen how to multiply exponents, or you also should have seen how to multiply exponents in some other classes. So hopefully this is a review. If not, here we go. So to make this happen, you are going to add the exponents, and you are going to multiply the coefficients. So remember, our coefficients are these guys right there, and then you're going to add the exponents. So you can see that that's kind of what they have set up here. So you're going to add the exponents together, you're going to multiply the coefficients, and here's your answer. So that's basically kind of how the rest of it goes. But two monomials with multiple variables, so it's the same thing. It's just that you have to line up your variables. So again, your coefficient, 2 times 4, is going to be our 8. So you see that right there. So then our a to the 3 and our a to the 6, you're going to add the exponents together. So there you go right there. And then the 4 and the 2. And then you'll end up with this guy. So remember, the exponents are added together and the coefficients are multiplied. So things get interesting when you get into the binomials or even polynomials. So I'm pretty sure we'll see polynomials later on, but our binomials, so you're basically going to end up foiling it out. So there, 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 and we'll go over a couple of ways to organize that. But then as you hit, x times 2x, you're going to add the exponents. So that would be 2x squared right there. So, you'll hit 3, -1, so that's -3. And then when you you'll have 6x here, and then -x there. So then you'll get that 5x. So we've done all of these things before. Now we're just kind of adding them all together. So I don't know if that's going to help or not, but we'll see. So they've got two different techniques. They named them, I guess. So there's Cam's method, which is also the vertical method. I would rather you remember the vertical method as opposed to Cam's method. I mean, who's Cam anyway? So the vertical method is you, again, line up your polynomials. Actually, we can even zoom in on this a little bit. Or not. And then, so they started with the 7. So they took 7 times that one, 2x squared. You get your 14x squared. 7 times 7x, 7 times x. 7 times -4 is where you get this first one. And then their second line is x times 2x squared, x times x, x times -4, and then you add them together. So very similar to if you'd like do the multiplication of larger numbers, same concept here. So you're just going to multiply each one by each of your numbers on the bottom part, numbers or variables on the bottom part, and then you're just going to add them all together here. So they also have a written out step-by-step process. Technically, they don't have to be in standard form for this to work, but it's good practice to get into to put everything in standard form. Just an FYI. So the horizontal method is, actually the horizontal method is what you would use in a quote-unquote proof. So here's where you start. So you, again, you write it in standard form because why not? So because of the distributive property, you can, I don't want to say pull the x out, but this is x times this whole thing right here. And then you can add, right there, 7 times this whole thing right there again. So then you just do all of that math, so x times 2x, x times x, x times negative 4x, that's where all of this stuff came from. 7 times 2, 7 times x, 7 times negative 4, and done. And then you just combine like terms. You get the same answer either way you do it. Both ways work. Both ways are mathematically sound. You don't have to know how to do both ways. You just have to do it correctly. Again, I don't care which way you pick, as long as you get the job done. So how is Cam's method similar to the vertical method for multiplying whole numbers? So we kind of talked about that. It's that same process of multiplying, adding, things like that. Which method do you prefer and why? That is entirely up to you. So let's try some examples. Hey, so we're going straight into a real world example because you have plenty of examples in your homework. So model with polynomial multiplication. So Amber opened a cell phone repair company in 2000. From 2000 to 2020, the function n of t that models the annual number of cell phone repairs in thousands, and the function c of t that models the average cost of the repair in dollars, are as shown in the photo, where t is the number of years since 2000. Find a function r of t that models Amber's total annual revenue from cell phone repairs. Then use the function to estimate Amber's total revenue in 2015. So we've got a model that annuals the number of cell phone repairs, and that models the average cost of the repair. I assume that's how much she's charging. And so the total number would be the total revenue. I guess she has zero costs. I don't know. Would be our function times each other. So that's how many phones she repairs and the number that she charges, the amount of money she charges per phone. Multiply them together and you will have your total annual revenue. So we've got our two functions here. And so we are going to multiply them together, right? So here we go. So this is just saying the same thing we did. Since the annual revenue equals the annual number of repairs times the average cost per repair, a function for the annual revenue, bam, bam, that's what we talked about. So they're going to show us the vertical method. So you set up your two equations right here. So technically, when we're multiplying, it does not matter which one goes on top, which one goes on bottom. I tend to put this smaller one on bottom, just if there's like less factors, but I don't know, that's just me. So they're going to work right to left. So 23 times this number, 0.69 t squared. minus 23 times this number right there, and then 23 times 2.1, is that going to be that guy right there. So then we're going to do this one, 1.1t times this number is all the way over here. And then 1.1 times negative 0.44 is right there. Make sure you're careful with your exponents. And then 1.1 times 2.1 is right there. Notice how as we're going through, we're already lining up exponents. So all of your single exponents, t's, are going to be right here. All of your coefficients by themselves, and then x squareds, x cubes, and x fours. So that's the exact same thing that you would do with like a regular multiplication problem. So then last but not least, 0.12 t squared times this one. We've got our t to the fourth right here, our t to the third, and then our t to the fourth. So just make sure you're lining up your exponents. That's very important. And then you just add them all up together. So that's kind of why it's important. So now it's very easy to see that 43 plus nothing is 43. Where are we? Negative 9.2 plus 2.31, and you're right here. And so they're just adding and subtracting all of the coefficients. So we've got our annual revenue of this function right here. And that is measured in thousands of dollars. And T is, what do they say, years past 2,000? Yeah, T is the number of years past 2,000. So to estimate the total revenue in 2015, you would just put 15 in for T in the equation. So here is our original equation. Go away, line. We just substitute 15 in for T. Plug that into your calculator. Boop, 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 boop. And then we get, you won't get this number, but the cost, where did it say? Cost of T, oh, in dollars. Yeah, okay. Not in thousands of dollars. Okay. So yeah, I was wrong. It's okay. So you will get this number, or something close to it. I'm assuming they're rounded, but whatever. So let's see what they got for us. Finn says that since R of 15 is 189.525, Amber's total revenue in 2015 was about 190, not 190,000. Why is Finn incorrect? Select all that apply. Yeah, I thought the average cost was in dollars. Oh, here it is. So the cell phone repair function, so the N of T function, is in thousands. So this function right here tells you the number of thousands of cell phones she's repaired. So that's why Finn is incorrect. So the function R of T gives revenue in thousands of dollars. So I would agree with that one. Revenue in thousands of dollars. In what year did Amber's total revenue first exceed $300,000? So now what we're going to do is we've got this equation, and we're going to, again, we don't have the mathematical or the algebraic ability to solve that equation, but basically we would. So we would set that equation equal to 300, because remember it's in thousands of dollars, and then we're going to pull up our calculator, which I of course wasn't ready for, but that's okay. And let's see here. So I'm going to write this down, 0.0036. I'm just using x's because that's what I'm going to have to enter into my calculator. 0.015x cubed plus 0.502 x squared minus 6.89x minus 6 point, nope, yeah, 0.8, oh, I already did that one. Plus 48.3. Okay, so I'm going to type that in. 6x to the power of 4 minus 0.015x to the power of 3 plus 0.5, let's get the right numbers, 502 x to the power of 2 minus 6.89 x plus 48. So we're going to get all my chicken scratch off. I'm going to write down 300. So then again, we're just going to trace. Apparently she started off having a bad year, which is common whenever you open your own business. But so we need to find where y is at 300. So I can just go up to here. And my x is going to be, we'll call that 17. So, and if we go back to the question, in what year did Amber's total revenue first exceed 300,000? 2017. And so that is one of those situations where at this point you just have to graph and let your calculator do the work for you. Okay, so now that we've used the multiplication of polynomials, now we can get into some proofs. This is good stuff. So we are looking at polynomial identities. So a polynomial identity, gee, it's bolded. Maybe that's something we should remember. A polynomial identity is an equation stating that two polynomials are equivalent. For example, the equation a plus b quantity squared equals a squared plus 2ab plus b squared. So this is a polynomial identity. This, I think, is, I mean, you should have seen this before because it's basically how we take care of these types of polynomials. But we can prove that that works by rearranging one side of the equation to make the other side. So there's two ways that we can prove it. You can either, first way to verify the identity is to start with one side and rewrite it until it matches the other side. Another way is to rewrite both sides until they both equal a third expression. So either way will basically prove a polynomial identity. So we can try it out. So it says verify the polynomial identity a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. So this side is already simplified. So I bet if we just simplify this side, we'll be in good shape. So we first use the distributive property, or a glorified version of foiling. So we would take our a times all of these things, our negative b times all of these things, and we would get something that looks like this. So a times a squared plus ab plus b squared minus b times the same thing. So then we distribute that all out. We get our a cubed, a squared times b, a b squared minus a b squared minus a b squared minus b cubed. So then you can start combining like terms, and you'll notice that there is an a squared b, a negative a squared b, positive ab squared, negative ab squared. So they cancel out and leave you with a cubed minus b cubed. So all we did there is we simplified the left side of the equation, and it now equals the right. Identity proven. And we did that by using, so the second step, we use the distributive property. Third step, we use the commutative property of addition, and that was just so that we could rearrange, combine like terms, things like that. Therefore, we have proved that this is a polynomial identity. Good job. Let's do it again. All right, we've got one more polynomial identity. And this one has something to do with something I hope you recognize, the Pythagorean theorem. I know you probably thought you'd never have to deal with it again, but here we are. If you remember, the Pythagorean theorem is with a triangle, a squared plus b squared equals c squared, when a and b are the two shorter sides of a right triangle and c is the hypotenuse. So we can actually use the polynomial identities along with the Pythagorean theorem and to do some cool stuff. So here we go. First, the polynomial identity x squared plus y squared quantity squared is equal to all that nonsense. So that's the first identity that we need to prove, and then we can use that identity to find Pythagorean triples. Verify the identity, then find the Pythagorean triple using x equals 5, y equals 4. So we'll get to that. So to verify the identity, instead of trying to make one side look like the other side, we are basically going to just simplify both sides and hope that they're the same. They should be the same, but we're going to make sure of that. So let's start with the left. So we've got that right here, x squared plus y squared quantity squared. So if we use that equation from the previous example, we've got x squared squared plus 2 times x squared times y squared, right there, plus y squared squared. So again, that was the identity that we proved in the last example. So x squared squared is x to the fourth. That stays the same, and then same thing, y squared squared, y to the fourth. So this is simplified. Okay, so now let's look at the right side of the equation. So we've got x squared minus y squared quantity squared. So again, we're going to use that same thing from our last example. So inside of these brackets, we've got x squared squared minus 2x squared y squared, and that minus comes from that guy right there. And then y squared squared, all inside the bracket. So then we got this to deal with. 2xy times 2xy is 4x squared y squared. So again, our coefficient got multiplied together, our exponents got added, and we're good to go. So we multiply everything, we simplify everything in brackets. Here's our x4 that came from that. 2x squared y squared stayed the same. This turned into y to the fourth. And looks like we have some similar terms that we should combine. So negative 2 plus 4 is a positive 2. And so here we go. We have that simplified. And then we look up here. It turns out it is the same thing on both sides of the equations. So we have verified that this identity is true. So now we can use it along with the Pythagorean theorem. So how is it the known identity a plus b squared equals a squared? So again, we use this, or we figured out this in our last example, and we just applied it to our x squareds and our y squareds and everything like that. So both sides of the equation simplified to the same thing. So the equation is an identity. So to find a Pythagorean triple using x equals 5, y equals 4, note that the identity, what we have, has the form c squared equals a squared plus b squared. So did you catch that? So if we look at this right here, it is that squared. So here's your c equals a squared. There's your a. And there's your b. Clever, right? So we've got c squared equals a squared plus b squared, or at least the same format. So where a equals x squared plus 2, b equals 2xy, and c equals x squared plus y squared. So find the values of a, b, and c when x equals 5 and y equals 4. So I already mentioned c squared, a squared, b squared. So we could then say the equation, this guy right here, a is equal to x squared minus y squared. Plug in the values, you get 9. So same thing for b. So let's see here. A squared, b squared is 2xy. Plug in the values, x equals 5, y equals 4. We get a number. So a equals 9, b equals 40. So c, we could either use a squared plus b squared to solve for c squared, or we have a nice little equation right here. C squared is just going to be x squared plus y squared. Plug in some numbers. There is our c squared. So the Pythagorean triple is 9, 40, 41. So what does that mean? That just means that, so for every triangle, A, B, C, for every triangle, there is a certain set of numbers that where A, B, and C would work with the Pythagorean theorem. So this is just one of those many different triples. So that's what's called a Pythagorean triple. So how can you check that 9, 40, and 41 is a Pythagorean triple? A squared plus b squared equals c squared. So theoretically we could take 9 squared plus 40 squared, and it should equal 41 squared. And I don't know if they're going to have us do it, but we could do it. Shouldn't be too hard. Let's do it. Might as well. So 9 squared plus 40 squared equals 41 squared. So 9 squared is 81. 40 squared is 1600. 41 squared is 1681. Look at that. A squared, b squared, c squared. Done. So they are, in fact, Pythagorean triples. Too easy, right? So that was our last task for this lesson. Try the check on learning. And of course, if you have trouble with them, check out my other video. If you don't have trouble with them, too easy, right? I'll see you in class.